precisely, a bomber on a military mission is flying horizontally at a height of 3,000 meters above the ground, 60 kilometers per minute. He drops a bomb on a target on the ground. Determine the acute angle between the vertical and the line joining the bomber and the target at the point of at the instant the bomb is released. Okay, now we are asking us to determine this angle that is marked there with this sign. Let me put it at the they say you should determine the acute and joining the vertical. Use the vertical and the line joining the bomber and the target. The line joining the bomber. See the bomber here means my caricature illustration. Yeah, this is the plane or the whatever. They say it's a bomber on a military mission. So it's as if the bomber is inside this aircraft. So the aircraft is moving at a speed of 60 kilometers per minute. It releases a bomb from this aircraft to hit a target on the ground. This is a target. So the angle between this vertical line and the line joining the bomber and the target, this is the angle here theta. So let me clean that and write it down. So this angle is what they are asking us to calculate. Now, before we can know the value of that angle, already we know the length of this vertical line, which is the height of the bomber above the ground. We need to know this horizontal line, the distance from the horizontal distance from where the bomber is to the target. We need to know that. And how do we know that? Now, aircraft is moving at a speed of 60 kilometers per minute, rather. Is that same speed the bomb is going to move with when the bomb is released? So in that case, if the bomb is released from this aircraft, of course, it's going to trace a parabolic path like this and then hit the target. So this parabolic path of the bomb, that is this line outside, they're hitting the target. So we are required to calculate the distance from the bomber, the horizontal distance from the bomber to the target. Recall that when something is released from a height, has two components of motion, the horizontal motion and the vertical motion. Now, the horizontal motion is dependent on the velocity of projection, which we learned in our previous class. And what is the velocity of projection here? The velocity with which the aircraft is moving, which is 60 kilometers per minute. Now, converting that to meter per second, because the distance above the ground here is in meters, so the unit must agree before we can do anything. So I have to convert this initial velocity, which is the velocity of the aircraft. I have to convert it to meter per second. Now we know that 1,000 meters makes a kilometer. Converting 60 kilometers per minute to meter per second will be 60 times 1,000 divided by, now how many seconds makes a minute? 60. So per minute means divided by minute, and 1 minute is 60 seconds. So divided by 60. The 60 will cancel out. So the initial velocity is equal to 1,000 meters per second. So this horizontal distance here, which is the distance from the foot of where the aircraft is to the target, is dependent on this velocity of projection, which is the velocity of the aircraft. And then this thing is coming down under from a height rather of what is it called? The height of 3,000 meters. Recall that the horizontal component of the motion is independent of acceleration due to gravity. So if we use the formula h, which is the height now, or s, okay, let me use that so you know that it's the equation of motion I'm using. S equal to ut plus half gt squared. Now, the horizontal component of this motion is independent of gravity. So this term here, which is half gt squared, will be 0. So first of all, we need to know the time taken for the bomb to fall from this height to the target, because we need that time in order to get the distance, the horizontal distance. But we don't know the time that the bomb will fall from this height to the target. So in that case, if we are calculating the time is independent of the initial velocity of projection. So it's as if the bomb is released from a height. Whether there is initial velocity of projection or not, when something is released from a height, it is expected that that thing will fall to the ground, yes or no? So when calculating the time taken for an object to fall to the ground, the time taken is independent of velocity of projection. You take it to be that, okay, that object is released from a height. And when something is released from a height, initial velocity is zero. So in that case, this first term here is zero because zero times t is zero. Now we know the height of the aircraft. The aircraft is at 3,000 meters above the ground. So 3,000 is equal to this first term here is zero. U times t is zero. So R times G is 10 and T is what we are looking for. So that 3,000 is equal to 2 here 1, 2 here 5, 5t squared. So that when we divide both sides by 5, t squared is 3,000 divided by 5. And 3,000 divided by 5 is 600. So 600. If t squared is 600, that means t is square root of 600. Square root of 600 is 24.5, approximately 24.5 seconds. That's the time taken for the bomb to fall from the target, that is from the aircraft, rather not from the target, to fall from the aircraft to the target. Now, this is just a means to an end. What we need is the horizontal distance, from where the aircraft is to where the target is standing, right? For us to get that horizontal distance, we need the time taken for the bomb fall from the aircraft to the target. That is the essence of calculating this time taken for the bomb to come out of the aircraft and down to the target. Now that we know the time, we can use that time now to find this horizontal distance. And this horizontal distance, as I said earlier, is independent of gravity, but dependent on the initial velocity of projection, which we converted to 1,000 meters per second. So in that case, using this same equation of motion, S equal to ut plus half gt squared, the first term here, which is ut, is what we are going to use. So in the second term, half gt squared will become zero because g is zero here. Horizontal component of motion is independent of gravity. I've been singing that right from our previous class. So in that case, we are looking for this distance now, horizontal distance, which you can call the range of the projectile. So let me call it R to differentiate it from the other S above. The initial velocity of projection is 1,000. 60 kilometers per minute is converted to 1,000. 1,000 times 24.5. 24.5 is already on the memory of the calculator. So times 1,000, that is 24,000. Let's do that one. Let's confirm that. Let's see if I type 10,000 instead of 1,000. 1,000 times 24.5. 24,500. 24,500 meters. So this distance, this horizontal distance is 24,500. 24,500 meters. Now that we know this, and this is given to us, we have to calculate this angle here. We are going to use SOHCAHTOA. The angle is here. This side facing it is opposite. The longer side is hypotenuse, and this third side is adjacent. So which of the ratio out of SOHCAHTOA? Let me write it down. SOHCAHTOA. Which of this ratio connects opposite and adjacent? That is TOA, tangent. So tan theta is equal to opposite, which is 24,500, divided by adjacent, which is 3,000. And 24,500 divided by 3,000, 8.1666, the recurring decimal, 1666. So theta will be tan inverse of that, tan inverse of 8.166, which is, my calculator does not have that option. Let's see. That's okay. Okay, I've seen it. So tan inverse of 8.1666, 8.166. We press this arrow here, then tan inverse of it, 83.02 approximately. The theta is 83.02 degrees. That is the angle between the bomber and the target.